Welcome back to lecture 2 of week 6. In the first lecture, we'll introduce the notion of a subsequence. Notice that subsequences are sequences in their own right. They just happen to be a part of a larger sequence. As sequences, we can take their limits. The numbers that result from this process are called subsequential limits. This lecture corresponds to material found on pages 68 through 70 and also 72 and 73 of your textbook. Just to clearly state the definition, we say that a number z is a subsequential limit of a sequence x sub n if there exists a subsequence x sub n sub k that converges to z. The definition of convergence of subsequence is basically the same as the one for convergence of a sequence. A subsequence x sub n sub k converges to z if for every epsilon greater than 0, there is a capital K, such that for every small k bigger than capital K, the subsequence term x sub n sub k is no more than distance epsilon away from z. Let's illustrate this by returning to an example we visited in lecture 1. The sequence cosine 2n pi over 3. As we discussed in lecture 1, because the term minus 1/2 and the term 1 each appear infinitely often in this sequence, there exists constant subsequences outputting each of the two numbers. And since the constant sequence converges to its constant output, this means that there is a subsequence, which is 1 for every term, that converges to the number 1. And there is a subsequence, which is minus 1/2 for every term, that converges to the number minus 1/2. And hence, minus 1/2 and 1 are both subsequential limits of this sequence. On the other hand, let's show that according to our definition, the number 0 is not a subsequential limit. To show that the number 0 is not a subsequential limit, we need to prove that there are no subsequences that converge to 0. Now, given an arbitrary sequence, unless it is the constant sequence, it generally has infinitely many subsequences. So we cannot possibly check all possible subsequences on a case-by-case basis. So we need to find a general rule in order to prove that a number is not a subsequential limit. So here's the idea, and this is the idea that we will generalize shortly for application to general sequences. For this specific sequence, we can argue by first noticing that there is an open interval around 0 into which the sequence x sub n never enters. Let epsilon be equal to 1/4. Then, since the sequence only takes values minus 1/2 and 1, the sequence never enters the interval from minus 1/4 to plus 1/4. As the subsequence is only ever made out of terms from the sequence, this means that if the sequence never enters an interval, the same is true for any of its subsequences. And hence, no subsequence can enter into the interval from minus 1/4 to plus 1/4. And with this, we have exhibited an epsilon such that any subsequence never gets within a distance epsilon of 0. And this is precisely the statement of 0 not being a limit of any subsequence. We can codify the method using the previous slide for the detection of subsequential limits into a theorem. A number z is a subsequential limit of a sequence x sub n if and only if, for every epsilon positive, the set of indices n for which x sub n enters within epsilon of z is an infinite set. What is the difference between a subsequential limit and a limit? A limit has the sense of point of no return. For a limit, there is an index capital N after which the sequence can no longer leave the immediate environs of the limit. A subsequential limit is a bit more lax. All it requires for a number to be a subsequential limit is for the sequence to keep coming back and getting close to the number. the sequence is allowed to get far from the number for some time before coming back. The key is that a subsequential limit somehow attracts the sequence, forcing it to return over and over, even though individual visits may be brief and the sequence may choose not to stay. We will prove the two directions of this theorem in this and the next slide. In this slide, we prove the implication that if z is a subsequential limit, then the set of indices for which x sub n comes within epsilon of z is infinite for any epsilon positive. To do so, we use the definition of subsequential limit. If z is a subsequential limit, there is a subsequence that converges to z. For any epsilon positive, there is a capital K such that for any k greater than capital K, the term x sub n sub k is no more than epsilon from z. Now, the sets of outputs of n sub k, corresponding to k greater than capital K, is a subset of the indices for which x sub n is no more than epsilon for z. Since n sub k is strictly increasing, the corresponding function is injective, and since there are infinitely many small k bigger than capital K, this means that there are infinitely many indices for which x sub n is within epsilon of z. And this is what we aimed to prove. Next, we prove the reverse direction, which is the implication that if the set of indices is infinite for any epsilon positive, then the number is a subsequential limit. To do so, it is enough to construct a sequence x sub n sub k that converges as k goes to infinity to the desired z. What we will do is choose n sub 1 to be the first index for which x sub n is within distance 1 of z. We then pick n sub k recursively. Having picked n sub 1 through n sub k, to pick n sub k plus 1, we look at the set of all indices for which x sub n is within 1 over k plus 1 of z. We discard from this any indices which is less than or equal to n sub k. And we choose the first index from the remainder. This remainder is non-empty because we know that the set of all indices for which x sub n is within 1 over k plus 1 of z is an infinite set by hypothesis. And there are only at most finitely many indices that can be less than or equal to n sub k. So there are still infinitely many left over after discarding. And so there is at least one that I can choose. By our construction, this index must be larger than n sub k, guaranteeing that the selection function is strictly increasing. This way of building n sub k guarantees directly that x sub n sub k converges to z. For epsilon positive, by the Archimedean property, there is some capital K such that 1 over capital K is less than epsilon. If I choose small k bigger than capital K, our choice will have that x sub n sub small k is no more than 1 over small k distance from z. Since 1 over small k is less than 1 over capital K, which is in turn less than epsilon, this shows that for all n sub small k with k bigger than capital K, the term x sub n sub k is less than epsilon away from z. Since epsilon is arbitrary, this proves precisely that the subsequence thus constructed converges to z. Let's finish today by doing two examples using this theorem. First, we have the sequence that looks like 1, 1/2, 3, 1/4, 5, 1/6, 7, 1/8, and so on. So on the odd terms, it looks like n, and on the even terms, it looks like 1 over n. Since the odd terms grow unboundedly, this sequence cannot converge. Let's look at the subsequential limits of this sequence. First, we find that 0 is a subsequential limit. This is because the even terms looks like 1 over n, which tends to 0. To make this rigorous and precise, let us give a proof. Based on the theorem we just discussed, it is enough to show that for every epsilon positive, there are infinitely many terms of the sequence that are within an epsilon distance from 0. So, set epsilon positive. We see by the Archimedean property that there is some capital N for which epsilon is larger than 1 over n. We see that for every small n that is both even and greater than capital N, the term x sub n is positive and less than epsilon. Since there are infinitely many even numbers bigger than capital N, we conclude based on the fact that epsilon is arbitrary that the theorem can be used and 0 is a subsequential limit. Next, since the theorem is an if and only if statement, we can also use the theorem to determine when a number is not a subsequential limit. Let us prove that any positive value cannot be a subsequential limit. Take a to be a positive number. In order to use the theorem to prove that a is not a subsequential limit, we need to show that there exists at least one positive epsilon, such that there are only finitely many terms of the sequence that sit within distance epsilon from a. What we can do is to take epsilon to be a over 2. Then the interval we hope the sequence will avoid is the interval from a minus epsilon to a plus epsilon. This interval is the same as the interval from 1/2 a to 3/2 a. By the Archimedean property, we can certainly choose an index n such that 1 over n is less than 1/2 a. And we can also choose an index such that it is bigger than 3/2 a. Taking the larger of the two indices, we find a capital N for which we can guarantee 1 over capital N is less than a minus epsilon and a plus epsilon is less than capital N. Now, if small n is an index beyond capital N, then the term x sub n is either, if n is even, 1 over n, or if n is odd, n. In the former case, when n is even, it is less than 1 over capital N and hence less than a minus epsilon. In the latter case, when n is odd, it is greater than capital N and hence greater than a plus epsilon. In particular, we have shown that whenever small n is larger than the chosen capital N, the term x sub n has to be outside the interval a minus epsilon to a plus epsilon, which means it has to be more than epsilon distance away from a. This shows that the set of indices for which x sub n is less than epsilon distance away from a must be finite, since it cannot contain more than capital N terms. And this shows that a is not a subsequential limit of the sequence. It turns out that a similar argument can also be made for a negative. I'll leave that case up to you to work out yourself. Let us finish with a non-explicit example. For this example, we need to remember that sequences can also be regarded as functions from the natural numbers to the real numbers. We shall take as our sequence any bijection of the natural numbers with the rational numbers. Remember that in the beginning of the course, we discussed how the rational numbers are countably infinite and that there is a bijection from the natural numbers to the rationals? There are in fact infinitely many such bijections. For our example, it doesn't really matter which bijection we use. The example works for any of them. My claim is that when a sequence is defined in such a way, as a bijection with the rationals, then every real number alpha is in fact a subsequential limit of x sub n. We will again approach this using the theorem discussed a few slides ago. And hence, we wish to show that within any distance epsilon of any alpha, there are infinitely many terms of the sequence. But this is not too hard to see. For an arbitrary real number alpha, and for an arbitrary positive epsilon, the interval alpha minus epsilon to alpha plus epsilon contains infinitely many rational numbers. This is a consequence of the density of rational numbers in the reals, which is itself a form of the Archimedean property. Now, since X is a bijection with the rationals, this means that for every rational number that is within the distance epsilon of the number alpha, there is a single corresponding index. Hence, the set of indices for which x of n is not more than epsilon away from alpha is also an infinite set. An application of the theorem then tells us that alpha is a subsequential limit. If you think a bit about this result, you should see that it is rather striking. Any infinite sequence contains countably many terms. Since the terms of a sequence may be duplicated across different indices, the values reached by the infinite sequence can be finite, but it cannot be more than countably infinite. However, we see that it is possible for the sequence to have way more than that many of subsequential limits. In fact, in this example, we see that any real number which form an uncountably infinite set, which has a lot more elements than the rationals, can be attained as a subsequential limit of any sequence that lists all the rational. This is a good illustration to the hidden complexity underneath the notion of subsequential limits. That out of a countably infinite list of numbers, we can somehow arrive at many, many more. However, it turns out that there are some limits to what a sequence can have as its subsequential limits. For example, there are no sequences for which the set of all subsequential limits is exactly the rational numbers. And there are also no sequences for which the set of all subsequential limits is exactly the open interval from 0 to 1. We will be examining more about this, the structure of sets that can arise as subsequential limits of a fixed sequence in lectures 4 and 5. But we will have to take a quick detour in lecture 3 to cover a related concept. See you then.